let's talk about Riemann sums. So let's start with the basic function of just f of x equals x, right? Y equals x, the linear function. When y is 1, x is 1. When x is 2, y is 2, right? Simple, just straight up. And let's say the upper limit of this is 3. Okay, we could also define it like this. We could do 3 and 0. That will give us like a range if we wanted to, right? We do 0, 3. So this is the area that we care about. I'm just going to do x equals 3 just for ease of visual. And we're going to say in this Riemann sum, we're going to have three segments. 1, 2, 3. We're going to have 3 segments. So the first one will look like this, the second one will look like this, and the third one will look like this, right? And I can look at these and imagine the height of each one of these is going to be these intersection points, right? That's the height of each one. So there'll be 1 wide, right? 1, 1, 1. And then this one will be 1 tall. This will be 2 tall. This will be 3 tall, right? So 1 plus 2 plus 3 is 6. So the total here is 6. And by the way, if I wanted to kind of draw these out, I could do something like this, right? And actually draw out those individual boxes. So I have this defined here. And in my calculator, we talked about, all right, if I plot this, right, if I just do y equals x and graph it, I have that. And whenever I find the definite integral, meaning like the true area, right, if I go second calc, I get the true integral of the lower limit at 0, the upper limit at 3, it's 4.5. It's 4.5, right? But we know that that's not the same as the Riemann sum in regards to a 3-segment version, right? That is the sum if we were approaching the limit as it approaches. If we were taking the limit at infinity, right, as it approaches infinity, that's what gives us this value, and we will learn how to do this. But what we need to do is we need to figure out, well, how do I create a function that gives me the sums of these values, the Riemann sums of these values, right? Because that's what we're working with here. And for now, we're working with 3. We've actually seen the function that does this. Okay, we've actually seen the function. The function was that n plus 1 over 2, so it looked like this. It looked like x plus 1 over 2. It's this function. What? Yeah, this is the total sum function of this purple line. Here, I'm going to turn these guys off just for now, except for 3. So at 0, there's 0 of them. At 1, there's 1. At 2, there's 3, right? So if I go right here, there's 3. And at 3, there's 6. Right? There's 6 of them. So this is the correct function. And we saw this before where it was like in parentheses in, and x being the number of segments, right? And the width of those segments. So how did we actually derive this? How did we get to this function? Let's talk about it, okay? And the way we're going to talk about it is we're going to think about this as a triangle. All right, now there is a true triangle here, right? This 0 to 3, that's the hypotenuse. We've got this 3 to 0 over here. That's the side B. All right, then we've got this to this. That's the other side. So yeah, we've got a basic triangle here, which we can just simply do 3 times 3, which is 9, divided by 2, 4.5. That's the definite integral, though. That is not the Riemann sum. That's solving for this triangle right here. So how do we solve for the sums based on the number of segments that we picked? Okay, how do we solve for that? So I want you to think of it like a triangle, but like the stair-stepped triangle that we drew before. Okay, like the stair-step triangle that we drew at the beginning whenever we were working with the circle. I'm going to just draw this here. So what does this triangle look like? Okay, it comes over, then down 1, then over, down 1, then over, then to 0. Right? This is our triangle. And the way that we're going to think about this, the proof that we're going to have is we're actually going to turn this into a rectangle. I'm going to take this is my function. I'm just going to draw the red line. That's my function. But what I care about is this total area. I don't really care about the red line that much right now. I care about this total area of my Riemann sum. So how do I solve for this? I'm going to show you a technique, and this is using a geospatial solution. What if I turn this into a rectangle? I just take this and I duplicate it, right? I'll call this one A, this one B, right? I took it and I just duplicated it. Because of its shape, it can equal a rectangle. We know rectangles are easy to solve for, right? We can find the areas of those. And we also know that this space, because we took this and mirrored it, is exactly 1/2 of the rectangle, right? It is exactly 1/2 of the rectangle because we took the rectangle and duplicated it. So how big is this rectangle? Well, we know it's 4 this way, right? I can count 1, 2, 3, 4, right? Because I took this and I flipped it, it's going to be 1 more than my last, right? My last one is 3 high. It's 1 more than that. And then how wide is it? Well, it's 1, 2, 3. It's 3 wide. Okay. So it's 4 by 3. So I could literally write this out. 4 times 3, which is 12. And then I divide that by 2. And that gets me 6. Right? By dividing by 2, I'm just multiplying it by half. That gets me 6. And that is the answer for how many squares there are here, right? There's 1, 2, 3, 4, 5, 6. So these functions have a defined Riemann sum function that it's a summation function is what they call it. In particular, if the function is x, right? If f of x is simply equal to x, it's the linear function. We need to take the number of segments we have. I'll define that as n. That's how it's commonly defined. N segments. Okay, that's this right here. Right, we have 3, so that's n. We're going to multiply it by 4. Well, that 4, what is that? That is the n plus 1 we were looking at before. Times n plus 1. 3 plus 1 is 4. And then because it's half the size of our triangle, or sorry, our rectangle, we multiply it by 1/2, right? How could I rewrite this so it's a little cleaner? I could just put it over 2. This is what we were missing today, this divide by 2. And I mentioned a few times, I said, oh, we're missing something to divide by. Divide by 2. Let's think about this. Does this work in every situation where f of x equals x? Let's take another number. Let's take 7. Okay? So 7 would mean that my highest point is 7. So 1, 2, 3, 4, 5, 6, 7. All right, so that's my highest point. And then 1, 2, 3, 4, 5, 6, 7, because that's my interval. My interval is 1, right? My delta x. And it would look like this, right? This comes up and up and up and up and up and up and up, right? How many boxes do I have in here? Well, I could count them, but I want to write a function that does it for me. And guess what? This function is going to do it for me. Again, my function is f of x equals x. All I have to do is just rethink of this. If I flipped and mirrored this, how would this work? Well, it would go up by 1. Right, if I turn this into a rectangle, come all the way across, then come all the way down. Boom, I have a rectangle. And it's mirrored, right? This is 1/2 of this, or 1/2 of the whole thing. So how tall is that rectangle? Well, that rectangle is going to be 1, 2, 3, 4, 5, 6, 7, 8. 8, aka n plus 1. Right, the number of segments I have plus 1. It's always that in this case whenever we have the 1 interval. And then I've got 1, 2, 3, 4, 5, 6, 7. Right, it's n wide. And it takes up how much space? 1/2. So we plug it into this formula. Let's do it. 7 times 7 plus 1 over 2. 7 plus 1 is 8. 7 times 8, 48. Divided by 2, 24. Let's count and see if my mental math was correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. 28, I'm sorry. 7 times 8, 56. 56. I said 48. 56. Sorry, that's 6 times 8. 56 divided by 2, which is 28. My apologies. I just did that math totally wrong. But you got the point, right? This turns into an 8. 7 times 8. And then we've got divided by 2. So this works for this whole function. Every time you plug this in, let's go to the calculator and see what that looks like. So again, remember, this is the definite integral, which we're going to learn how to calculate later. But for now, we're just going to do x. Okay, and for our second function, we're going to do x times x plus 1. And then all of that over 2. Over 2. And let's graph. Whoa. What is this function? It's a parabola. And if I look at it, does it line up? So at 1, there's one segment, and it's 1. At 2, we're at our second segment. It's 2 wide. The first segment was 1, so 2 plus 1 is 3. 3. The next one is 6, right? 3 plus 3 is 6. The next one is 10. 4 plus 6 is 10. The next one is 15. So you can use this function and find anything, right? I can find, okay, at 22, this is what, with one segment each, with delta 1, delta x equals 1, that is what I get.